Hello all. In this video I would like to teach flow over a circular cylinder in two-dimensional, means flow over a circle using different softwares for pre-processing, processing and post-processing. Let's go to the video. First we need to open the Gambit software for the meshing. I will browse the corresponding directory for the machine. So I created a folder flow over a circle for this one. So we need to open the Gambit in the corresponding directory. Okay, Gambit is opening. So in my previous video I given the steady state problem. First video is flow through a two-dimensional pipe and another is flow through a square cylinder in steady state. Today I would like to give in unsteady conditions like continuous flow. Will work on the geometry creation. Let's take a circle. Okay, we'll use like 1 unit of diameter, so the radius should be half of the diameter, 0.5. Let's create the body. Okay, then we will create the domain in like in x direction. We will keep this as a like 10D and y will keep as a 8D. Okay, sorry, this has to be the -10. Okay, similarly here also it has to be a -8 at the bottom, right? We will keep 20 times in the arrow direction. So okay, this has to be 8. Okay, we will have the bigger domain for the flow analysis. Okay, let's create the outer domain using point to lines, then line to face. These are the basic steps in the Gambit. Then we need to create the face using apply created. Then we need to separate the face from bigger to smaller. Since we need to consider this as to a single face for the computational domain. We do, to check, yeah, we can see only one face as created based on separation. Why means like we no need to have the mesh inside the cylinder. Okay, right, done. We can see this is the two-dimensional cylinder enclosed in a flow area. Okay, let's enter into the domain. Like first we create the model, then we need to give the boundary conditions in the solvers in the meshing software itself. Okay, let's take, this is the velocity inlet. Okay, this has to be in the last. Okay, velocity inlet. Okay, apply, right? Yeah, we'll check created or not. Yeah, it's created. This has to be a pressure outlet. Okay, then apply the top, bottom has to be a wall. Sorry, caps on a wall. Okay, apply. This has to be a wall. I will give him this as a circle, right? Yeah, right now we completed the like domain creation also. Then we'll move to the mesh. So we will create a three-dimensional triangular mesh for this structure, just for understanding purpose. If you want to do the research or like full-fledged research on this one, you need to create a structure mesh for the efficient results. Even like we will get the good result here also. So for the edge mesh I will create here as like 0.01 interval size. Means suppose if you have a 10 domain, means it will create a 100 mesh. Similarly here edge mesh, we need to select edges. Alright, here what will give is like interval size 0.8 we will give, for just for understanding purpose. We are not going to doing a full-fledged simulations here. Sorry, a code it won't take. Okay, it's not taking. We'll move to the triangular. Must even number interval for the map. We'll go with the triangular. Okay, we'll create a triangular mesh based on our computational domain C. This is how the mesh is created in this one. Still you want like more refinement of the mesh, we can do in the fluent. We will increase 1 order or 2 order in the fluent. Okay, right now mesh creation part in the Gambit is done. We need to export the mesh over the corresponding folder. I will rename into the circle, right? Okay, accept mesh was returned successfully. Then we need to open into the Fluent software for the post processing. Yeah, 2-dimensional double precision. I will save this project right now. It's saved. We will close the Gambit for time being. Yeah, again it's asking save. Yeah, it's done. Now Fluent is opened. I think Gambit environment is also we can close. Yeah, we need to read the case. We'll check where the folder is floor square cylinder. Sorry, we need to redirect to this one, circle mesh. Yeah, we saved and we created the circle mesh. Like we'll check a grid check what's the domain and all. It's like showing. Okay, fine. It's in the meter. So meter means it's difficult. We need to convert this meter into a, like we'll change the unit here, grade scale or info size. How many cells is there? Like we have the very less number of cells. Then we will scale, and mesh was created in like let's take a centimeter. Okay, scale. Okay, close. Just for understanding purpose I reduce the domain. Now we'll grid check. We'll see here the unit is changed to 0.1. Previously it was 1. Okay, fine. We need to adapt further refinement of the mesh. Before that I will go to display. I will show the mesh, how the mesh is looking like. Display, this is how our mesh is looking. Okay, fine. I will keep this aside. I don't know how to merge this one, like page setup. True color print scale, vector, background orientations, enhanced meta file. Now those are the clipboard formats. I don't know how to this one merge both the software at the single stuff. Okay, let it be fine, right? Then we will do the adaptation region. I already explained to you to adapt, how to adapt the stuff. Number of cells is marked, adapt yes. So the number is like increased to the 4 times. Further one more time we will do the refinement for the better quality of the results. We got like right now 84,688 cells. Will one more time to display the grade, then you come to know how we are increase the, see how better the mesh is right now. So this will capture surely like better results compared to the previous one. Like okay, right now the mesh is imported perfectly to the Fluent environment, solver environment. Then we will do the basic settings over here. Grid we checked, define, we can do the models, solver settings. Right now we will keep the unsteady cases, time, first order implicit scheme we will use, like other second order least square cell approximation method we can use for the better results. Right now that we will keep the pressure based as it is. Okay, fine. Grade, define it's okay, file, define model is done. The solver settings is right now done, like define model and discuss what model we can do. K epsilon. Okay, right now we'll use the K epsilon model. Standard K epsilon model is enough for the turbulence level. We'll keep all the parameters is constant for the K epsilon. These are the different turbulent model. We will keep the K epsilon right now. There are 5 different models there. Spot Allmax, K epsilon, K omega. Right now we will keep viscous model as a K epsilon 2 equation model. We will select as it is. Okay, we can see the changes here. K epsilon, standard K epsilon and unsteady. 2-dimensional double precision, pressure based Navier-Stokes equation. These are the basic stuff you need to know from the CFD theory. Right now the definition is done for the both the cases, like solver and viscous. Then we will go to the material is obviously air will be there, no need to change the material. Right now operating condition is like normal gravity, so flow is running as direction is like y direction. We will give the 9.81 for this one. Like okay, fine, that's also done. Like define operating condition done. Velocity we will keep flow over like okay. Here the trick is, what's the velocity flow over a cylinder? We will keep like height around 50 meters per second. We'll see how the flow will be. Okay, set again. Kinetic energy and dissipation rate, they are giving like 1% is there. It will be fine, otherwise like we can increase to right now we will keep as it is, like a thermal no need of heat. So right now we changed turbulence is standard K epsilon model, and kinetic energy is very low energy. Okay, here also we are having like very low kinetic energy model we have. So right now we can change. If you want to do many research over here, you can change this parameter and different turbulence model, effect of turbulence on the flow over here circle cylinder. Right now for to understanding purpose, for the pre-processing and post-processing, I am teaching a small level only. You need to understand more. Pressure outlet as a pressure outlet, velocity as a velocity inlet, fluid as a air, and wall as a wall, circle as a also a wall. So boundary condition wise it's okay. User defined function we are not doing right now. Units, okay, no, we are no need to change the unit. Like a remaining model, mixing place, no need. Injection also we are not doing anything. Solver controls, solution control, it will be automatically there. Pressure, like all the stuff we can use the simple model, or like a coupled model, piezo model, coupled model. We will use a simple model for the understanding purpose. So okay, fine. solver control is done. Then initialization from the standard initialization model. From the velocity we can initialize kinetic energy, apply initialization from this one, close. Initialization is done. Monitors no need, animation also right now no need. I will like do the post processing in the TechPlot software, then we can do the stuff. Iteration, time step size we will give the 0.01 number of time step. Let's run the simulation into the like 1000 time step. 1000 into 1 means around 10 seconds it will be there, around I think 10 seconds. Yeah, correct. Fixed, and the number of iteration also 20. The data sampling for the statistic, yes, we will keep the mean and RMS for the data sampling, right? Okay, apply, close. Then before that we need to write the case and data for our reference. This is the usual step for me. We can change easily. Start circle underscore start OSTA hot STA hot start CZ. Okay, it will save both case and data for our reference. Sorry, I forgot to mention one more stuff here. Please watch the video carefully too. For the right, we need to set the autosave mode for saving samples, case and data. Case we can keep like 1000, data we'll keep as a 100 or 50 will be fine. Like let's take 100. Flow rating no need, we'll give the name end circle. Okay, no need of start, right? Okay, now again we will write the case and data initially for our stuff. Okay, yes, we are rewriting the case and data. Right now the solver setting is done. Like we will run the, we'll iterate the simulations. Okay, iterate started. Simulation is started right now. So simulation is going smoothly. Operating, so it will have the some more time step for the simulation. Right now I will pause the video. After the simulation is completed, I will resume the video for the further. Okay, dear friends, the simulation running was completed. So the total flow time is around 10 seconds. So we will see the post processing. Otherwise I will show some of the counterparts over here. Then we'll move to the post processing section in the Gambit software. Okay, so we'll see the velocity magnitude. This is how the velocity is coming. Yeah, we can see at 0 position where the stagnant position velocity is like rapidly brings to the 0. Here we can see the backflow recirculation over here, kind of like a low negative. Here where this is the velocity magnitude point, you can see this is for the simple cases. You want like you can run like more different Reynolds numbers based on the velocity input. This is to understanding purpose only. For one, just I'm giving few insights to the simulation. Okay, you need to explore more for this one. I will show some other parameter over here. These are the velocity information like x direction, y direction, velocity, like that. Whatever parameter you can see the statistics nothing but the mean information, mean RMS velocity field for this one. So I will show the mean velocity field how it's looking like for the 10 seconds. See, this is how it's looking like. This is for the mean images of 10-second flow over here. Over a circle. Okay, here you can see the quite symmetric nature at x and x as well as the y direction. We can see the symmetric about this one. So here we can see the lower velocity, that too in negative zone. It's showing that the negative velocity means it's having the recirculation zone over here, the blue color indications. So at the starting point, the stagnating point where velocity is around 0, we can see the origin. For the mean plot, this is the negative velocity showing here. Similarly, for RMS information also we can see. I will show the RMS velocity field. Here we can see more turbulence involving here, the more RMS will be there at the behind the cylinder. Okay, these are the few counter plot. If you want, you can export to the proper shape. Then I want to show some vector files over here, like we'll see how it's looking like. Okay, fine, we will zoom this particular area to see the vector. Yeah, we can see. So here this is a negative vector, I told, right? Symmetric about them both. You can see the vector, it's rotating. I will show the path line for this one, then you come to know how the path line. So this will take time. Anyway, I will try to show display plots or display streamlines. We will go with the path line itself, right? Yeah, okay, fine. Okay, I will skip some 200 point, then just for okay, select all path caution. We will caution much more display. I already told you, right? It will take long time to show you. That's what here we can see. This is a path line. This is the wake region behind the cylinder. You can see how nicely it's forming the wake region behind the cylinder for this corresponding Reynolds number. So these are the cases we can what are the information you can need. You can plot it like XY plot, all the stuff. So I will show some of the interesting stuff in the TechPlot software for the post processing. So I will open the TechPlot. Okay, fine, TechPlot is opening. So load the KSM data. So here the data is from here, then okay, right? So it's asking compressing, no need to compress. It's loading. Casing, duplicating the zones, it will take some time to load. Okay, it's loaded. Before that, first initially we will do the axis alignment, then it will go and reverse axis. Okay, right. Ticks, it's outside for both x and y, then it should be good. And line, we'll have the marker line close, and range minus 0. Range in the y direction, it up to 09 or 08, right? Okay, we can have the nice contour over here. This is the pressure contour. Pressure will be maximum at stagnation point where the velocity brings to the zero. Okay, right? Yeah, we'll see the video next step. See, this is how the pressure is oscillating for the 10 frames. Then I will go to the mean pressure. Actually, we saved the mean information also. It's also following the same trend, similar trend. Okay, then like we will calculate the some other parameters such as velocity and vorticity for this one. We'll see how it's look like. This is velocity magnitude computer. Okay, fine. Then I will go with the vorticity also to understand how the vorticity will be there. Vorticity vector, vorticity magnitude, vorticity. We will calculate that also, no problem. Then what other parameter we can calculate is most of vorticity magnitude, right? Yeah. Okay, we'll go one by one from the velocity magnitude. This is the velocity magnitude for different. So anyway, I will zoom it here. Okay, we'll do it in the plot. Okay. So okay, fine, this will be fine. Okay, right? Yeah, you can see how the velocity is varying over there. And streamline, I will plot it. Okay, fine. In the back direction, this will be looking good. You can see how the back side recirculation is happening. We need to run the more, like I will delete the recent cases, delete all, close. I will do the smaller selection over here. Then you can see. Anyway, I will select over here also. Yeah, you can see how the backside recirculation zone flow over a circular cylinder. Here we can see the flow will go here also. We can plot it. That is not a big issue. See, we are getting right. So we can have the different color over the lines and all. Here these are the stuff, lines, ribbon and lines. Which color you want, you can put in the white color also, but black will be the good color for understanding stuff. You are getting right. Animate time. Okay, you are getting right. So we need to save this, means like this is in the on screen. We can do in the file. So AVI format, current image. Okay, fine. Okay, AVI or which format we can save? We can save MPG4, AVI also fine, right? Okay, fine. Okay, animation for circle. Okay, right. Just animation, we will put animation. Save. Okay, it's saving by frame. Once it's over, we'll see the animation. The animation can be used for the presentation, like to give the animation in the video. Okay, animation is done. We'll second the file. We'll see. This is animation. We'll see how it's playing or not. Yeah, it's very slow, so we need to increase the frames per second, right? Animate to a file on screen, frames per second, 12 frames per second. Here we'll reduce the frames per second to 1 frames per second, then it will come to the 10 seconds of the numerical simulations. Okay, then on screen on it we'll save in the file. Sorry, I closed it. Time, yeah, animate to a file, animation time 10 frames, not 1 frames per second. Again the this one that on it, animation 1 fps, 1 fps, right? Yeah, it's saving. Yeah, done. We'll see the animation once again. It's coming the same, I don't know, we'll see. Yeah, now we can see the different time frames in the simulation. I forgot to add the time on this in this slide. Let it be. I will add the remaining. I will like further improve the this presentation in the legend. We'll keep this as vertical one, vertical horizontal only. That whatever it says in this one, like then we'll bring this to here. Anyway, and the time. All right, insert text. Okay. Time is equal to ampersand symbol into this one, so solution time, okay, into seconds, right? Seconds or microsecond, I think second. Okay, it's taking this much of digits, size, points, color and line spacing, text box, frame, position, points by frame, text box, no fill option, that's correct. Okay, it's giving this much of digits. Okay, fine, let it be. So this is another, we can save based on that time. I will do it again one more time, saving 1 frame per second to the file. We will replace the file. Sorry, again I closed the stuff. Okay, animation to the file. Okay, on fps AVA the same. Okay, yes, I replace it. Okay, animation is done. How it will come based on the time, I think so. We'll see. Yeah, here we can see for every different time step how the simulation is, the flow is evolving, flow over a circle cylinder. Then what are the, what are the parameter you need, you can do vector also we can do over here. I will switch this one and I will zoom this particular area only, since like the backflow recirculation is the very negative impact over here. We are not able to see properly at this position, so further we will zoom it here, right? Okay, I will move some more little bit. Okay, right, then I will increase the size of the vector, then we come to know like a little bit plot and vector details, right? Yeah, correct. See, I will little more also we will zoom to understanding purpose only, right? Here you can see, now I will select this one. Okay, this is, it's looking more ugly. I will delete all the stuff placements, delete all, then I will create a smaller theme. Okay, just one click. Here also one click, right? Now that is also it one code. Okay, fine, I will delete it all. Here we can see the closer view behind the floor cylinder. You can see the recirculation zone, how the is rotating in this direction as well as this direction. So it's like recirculation is happening here. We'll see. So frame by frame, how it's changing frame by frame. You're getting right? Okay, fine. I'm stopping here. If you have any doubts, queries about the meshing, setting the solver and post processing, please comment me in the comment section. I will update you as soon as possible. Thank you for watching my video. This will be very useful for you. Thank you. Bye.